Hello, I'm Maria Santore. My group conducts research on interfaces. We study interfaces between materials and fluids and between pairs of materials. These can include polymer molecules, adsorbed polymer layers, films, coatings, and hydrogels. They can also include polymer and silica particles, cellulose fibers and glass fibers, and even the surfaces of biological cells. We're particularly interested in dynamic interfacial behaviors on the timescales of seconds, hours, and days that translate to new material properties and advanced material functionality. I am particularly interested in systems governed by weak reversible interactions. The energy associated with this is small, like that in the environment or in the air around us, and the forces are about 1/1000th that imposed by gravity, but the interactions are still strong enough to drive phase transitions, to assemble dynamic complexes, and to enable us to manipulate small objects. Students in my group study the impact of forces on interfaces. They quantify and identify previously unrecognized interfacial mechanisms, they engineer new surfaces, and they create new materials.
I am studying micron-scale colloidal plates. These tiny flat particles exhibit Brownian motion. They have about the same energy as their environment. However, if you are to look closely enough, you can see the particles are not entirely random. They tend to try to line up.
When interactions are weak, adhesion is reversible and material structures can reassemble.
So the elastic interactions in these two-dimensional curved sheets are different from capillary interactions and can produce unique assemblies. You might think the structures will be disrupted by touch, and you'll be right. But I can create structures that assemble and make chains when I touch the interface using this tiny micropipette. The structures I assemble are unique in two ways. First is I can assemble structures far from the touching point, and with a single touch, I can structure the entire sheet. Second is I can create a variety of structures with a single material composition.
Besides synthetic materials, biological tissues respond to touch. This can even be the case for biological cells, and it's been well known for mammalian and eukaryotic cells. We're interested in how this plays out for bacteria, whose volumes are 1/1,000,000th that of mammalian cells. When bacteria touch a surface, they undergo changes that enable them to form biofilms. If we could understand and master these processes, we could create new biomaterials that could still adhere materials but resist biofilm formation.
Hi, I'm Alexandra. I recently joined the Santore lab, and I'm working on studying how bacterial cells feel the stiffness of the surfaces they touch. I'm currently working on making 50-micron hydrogel films of various cross-linking densities and functionalizing glass cover slips.
Much of the work in my lab focuses on the development of the science of new materials and new processes and new mechanisms, but we're also interested in translating these to new technologies. We envision responsive paints and coatings that are based on coacervates. We envision materials that undergo transformation and change energy forms, and we're also interested in cell capture.
Hi, I'm Mr. Han. I am developing a paper-based device to capture cells and DNAs from breast milk. As part of an NIH-sponsored study, I examine this interaction of cells with the polymer engineered surface. In addition to creating my device for this work, I am also adapting instruments that were developed by previous students in our group.
The dynamic curvature experienced by biological cells is critical to their function. In material systems, curvature and elasticities can be manipulated to create new morphologies. I'm studying how nucleation and crystal growth are altered by elastic forces at curved interfaces. So, molecular symmetry in thin crystals makes them flat, but they can bend cylindrically and while preserving zero Gaussian curvature. I explore this effect to select between hexagons and flower-shaped crystals.
Beyond academics, the students in my group work in industry ultimately. They work on materials and polymers and vaccine technology, and they also do some things you might not anticipate, like intellectual property, data science, and finance.
My work is supported by the Department of Energy. They are interested in how molecules and materials arrange and interact with energy. I will soon be working for Merck on vaccine technologies.
So these crystals are only 4 nanometers thick. I'm developing a method to to measure their response to imposed force.
I'm looking forward to collaborating with a microbiology lab.
I have successfully created contoured 2D elastic fluids whose structures arises from elastically controlled alignment of monodispersed particles.
I am hoping the device I make will enable a new route to early cancer detection and increase the lifespans of thousands of women in this world, especially those who live far from the healthcare facilities.
If you're interested in learning more about what we do, feel free to reach out. I'd love to hear from you.